So with Unit 5, we're going to go over this as a, well, I say we're going to go over that one as a class. We're probably going to go over all of these as a class, so this part doesn't matter. This is what we would have done had we broken out into breakout groups. So we're going to look at Unit 5, 6, and 7 FRQ, and we'll start off with that. Let me just get this part ready. This is Unit 8 stuff. We'll get it set up and ready to go. But Unit 5 FRQ looked a little bit like this. Okay. So let's look at this real quick. And I'm not going to do parts A, B, and C fully, but I'm just going to talk about it a little bit. This is a probability distribution. And you can see that here are the scores on one particular hole. So I guess known as the water hole. So he might get as low as a 3 strokes, as high as 7 strokes. And you can see the probability distribution of that. So random variable X represents Miguel's score on any given time of trying to do this water hole. Lower scores are better in golf. And it is important maybe to point this out, that if it's a context you're unfamiliar with, the AP test does not expect you to have this kind of background knowledge that says, oh, I know what I'm looking for. So make sure you read the full prompt. Like if you're not familiar with golf and you kind of get confused, then make sure you're reading to say, okay, lower scores are better, if that matters for the particular problem. So suppose one of Miguel's scores from the water hole selected at random. What is the probability that Miguel's score on the water hole is at most 5? So this is a pretty straightforward one. Again, I'm not going to go through all parts like with showing the full math or anything. But if it's 3, 4, or 5, that's fine. What's the probability that the score is at most 5? So because these are mutually exclusive categories, all I have to do is add the probabilities together. 0.15 plus 0.40 plus 0.25 gives us our answer. So that should be 0.8. Now it says show your work. You always, even though it doesn't say it, you always want to put a sentence with context. The probability is 0.8 that Miguel will score at most 5 on the water hole. Calculate and interpret the expected value of X. Show your work. So it's easy for a problem like this just to set up your problem, like set up 2 lists and then just say, I'm going to, do my 1 variable stats in order to get my answer. I'm taking a second to get logged on with my iPad. But remember, your expected value is just the probability of an outcome times that outcome itself, plus the same for every other outcome. And I'm trying to get logged on real quick. So to show our work for part B, what I'd want to do is I would want to show, and you can, I believe, let me double check before I say this definitively. It includes right here on your formula sheet the expected value of a random variable, this formula. So I can use that. You're taking the value times the probability of that value. So my expected value for X is going to be the sum of all of these X sub I times the probability of X sub I, which in our case is going to be 3 times 0.15, these two, plus these two, plus these two, all the way across. Now you might not want to show all of them. So 3 times 0.15 plus ... plus 7 times 0.05. And there's where you can find your expected value.
You're saying you can just do that using 1 variable stat?
Yeah, I mean, your calculator will do that for you automatically if you plug in your list and your frequency list. But of course, you can't just say, oh, I used my calculator. So you want to show your work somehow. Okay, and then the part C of this, okay, let me see. Okay, so this is, well, I mean, the question is, do I want to spend a bunch of class time on this? But let's go ahead and look at this because this is kind of a fun problem. Maybe you don't think of it as fun, but here we go. The name of the water hole comes from the fact that a small lake lies between the tee, where the ball is first hit and the hole. Miguel has two approaches to hitting the ball from the tee, the short hit and the long hit. The short hit results in the ball landing before the lake. The values of X in the table are based on the short hit. The long hit, if successful, results in the ball traveling over the lake and landing on the other side. The two approaches are shown in the following diagram. A potential issue with the long hit is that the ball might land in the water, which is not a good outcome. Miguel thinks that if his long hit is successful, his expected value improves to 4.2. However, if the long hit fails and the ball lands in the water, his expected value would be worse and increases to 5.4. Suppose the probability of a successful long hit is 0.4. Which approach, the short hit or the long hit, is better in terms of improving the expected value of the score? Justify your answer. All right. So he's got a, all right, how would we do this? All right. I remember doing this one before, but now I haven't looked at it in half a year. Okay, so let's look at this again. His expected value, the average value that we would expect, is 4.2 with the short hit, or with the long hit. However, if it fails and lands in the water, his expected value would be worse and increases to 5.4. All right, so we can create a probability distribution from this. The probability of him successfully making the long hit is 0.4. So if you can work with me on this, let me try and get all this on the screen at the same time. All right. So we have a new probability. I'll just call it Y, just to make it different. So he might get 4.2 as his expected outcome, or 5.4 as his expected outcome. And the probability that he gets 4.2, which is better, depends on the successful long hit. So there's a 0.4 probability of this being the case and a 0.6 probability of this being the case. So now we can come up with our new expected value from this. So that's just going to be, well, that doesn't equal this, I should clarify. So we can come up with our expected value of Y, which is 4.2 times 0.4 plus 5.4 times 0.6. All right, so I got an expected value from this is 4.92.
When we have to find the expected value of the previous question.
Yeah, in which case we would want to know the expected value of the first one. Okay, so I mean, I'll just do this real quick in my calc. If you know how to do it, we can just understand that. I'm just going to plug this in real quick. Okay, so now if I do my one variable stats with this, I got an expected value of 4.55. So we start with here, expected value for X of 4.55. So as it is it worth it to try the long hit? No, it's not, because we're going to have an expected value of 4.92. And this is where knowing that lower is better. 4.55 is the better outcome. So expected value with the short is 4.55. The expected value with the long is 4.92. Okay. So here's what we can do is what values of P will make the long hit better than the short hit in terms of improving the expected value of the score. So since we know that this outcome 4.92 is based on this equation, we're saying, well, let's change these probabilities here and here. And since this is the outcome that we're kind of measuring it against, here's the basic idea. Algebraically speaking, I want to figure out for what value 4.55 is my baseline. So 4.2 times the probability, I'll just put P, plus 5.4 times 1 minus the probability. So are you guys mathematically seeing what we're doing here?
Yeah.
Okay, we're figuring out what probability will make us break even so that it's exactly as likely to get a 4.55 with the short or the long. So then we can go through, do the math, and we can figure out that's going to be 4.55 equals, let's see, 5.4 minus 1.2p. And then we can just solve from there. I know I
Wait,
just,
1.2?
Could
yeah,
you
I
go
just
over
condensed.
quickly how you got those numbers?
Yeah, I can do that in here. Basically, if I multiply that out, that's 4.2p.
Yeah.
And then this, I have to distribute that. So that's going to be plus 5.4 minus 5.4p. So then I just combine like terms. So that's how I got my
Oh,
5.4 minus 1.2p. And now we can just solve from there. So what I got for P is 0.708. So this is the probability of making the long shot that you would have to be able to get in order to even justify going for it over the short one. Okay. Is this a difficult problem? I think it has difficult elements to it. Mathematically, none of this is challenging, but knowing what math to use is the challenging part. Okay, but does that make sense? Okay, so maybe, I mean, typically I try not to go through every part of the FRQ, but I think this was worthwhile to go through the whole thing. All right, so then we had these two FRQs. And again, let me zoom in a little bit. We can look at this. All right, so this one actually isn't as bad. So we were looking at basically a fraud detection system that looks at a lot of transactions, and there's a specialist. So here we go. Based on past history, the specialist blocks 40% of suspicious transactions. Assume a suspicious transaction is independent of other suspicious transactions. So we're assuming every single transaction that's reviewed is completely independent. Okay. Suppose that a specialist will review 136 suspicious transactions in one day. What's the expected number of blocked transactions by the specialist? Well, this is where we're finding the expected value. Another way of finding this is just n times p. And so that's going to be, so it's 136 in the trial, 136 trials, and we could block 40%. This is p right here. Then we can just do 136 times 0.4. You'll notice in all these, one thing I'm skipping is the actual writing out of my explanation. But, you know, you could, it's up to you to make sure you can figure out how you would put that into your terms. We would expect, based on the probability of 40% and 136 transactions, that there will be 54.4 block transactions. Okay. All right, this is where it gets not more challenging, but where we just have to think through this. All right, suppose the specialist wants to know the number of suspicious transactions that need to be reviewed until reaching the first transaction that will be blocked. All right, anyone know what kind of problem this is? What kind of distribution we're looking at? Geometric, perfect. So that is, it is geometric because we're looking, you can even see the word first. We have, it's not a set number of trials, but how many transactions will it take until we see the first transaction on average? And since it's 0.4 probability, then what we can do, you can get the expected value here by doing 1 over the probability. And again, you don't have to have this memorized. This is very front page of your AP formula sheet right here. As long as you've identified it as geometric, then we can do that. 1 divided by 0.4 is 2.5. So on average, you would expect 2.5 transactions being reviewed until the specialist finds one that needs to be blocked. Now, defining the random variable of interest, we could say that random variable X is number of transactions until first to be blocked. And we would want to say in our description, how is the variable distributed? We could say this is geometric distribution. And that should be sufficient. I will say, and you shouldn't have to explain this, but a geometric distribution looks like this. It is not a normal distribution, but you shouldn't have to describe that aspect of it. Okay, now we can determine the expected value of it, and we can interpret the expected value in context. So we already did calculate it right there. So we did part B first, or part 2. And then interpret the expected value. We would expect 2.5 transactions on average. Now, any given day, it could be the very first, it could be the 10th. But on average, it will take until the 2.5 transactions being reviewed. All right, I've said enough on that. And the last one is consider a batch of 10 randomly selected suspicious transactions. Suppose the specialist wants to know the probability that 2 of the transactions will be blocked. The random variable of interest here will be random variable X is number of blocked transactions out of 10 trials. Okay. Now, what kind of distribution is this? It's going to be close to normal, but not normal. It's not T either.
Binomial.
You got it. It's binomial. Okay. So what we have is a set number trial. I'm just writing bins real quick. So it's binary. It's either blocked or not. Independent, that stated that. Same probability each time, 0.4. Set number of trials, n equals 10. So this is classic binomial. And this one is going to be approximately normal, but you have to have enough to make it look approximately normal. Okay. So to find the probability, you can do this with that formula that we learned, which is the probability that x equals exactly, capital X equals exactly 2 will be, so you can write it like this, n choose k. I'm going back, we're digging deep back into stuff that we did. You don't have to show, it's good to show the actual formula. And you can actually find it right here on your AP formula sheet where it says binomial. It gives you the probability, the PDF, binomial PDF. So it's 10 trials, 2 successes, and it's going to be 0.4 raised to the second power times 0.6 raised to the 8th power. And that is the actual calculation. But in practice, you can use binomial PDF on your calculator. So notice all I did was take that formula from the formula sheet. and put it into this.
Wait, why do we use PDF over CDF?
PDF because we're looking for the probability of exactly 2.
Oh,
If it was CDF, we'd say of at most 2. Yeah. So that's all for this one. Whew, you guys feeling overwhelmed already? What a Monday. Let's look at one more FRQ. Okay, let's see. Now we're looking at this one. All right, let me first of all zoom in a little. Zoom back out. All right, researchers are studying 2 populations of sea turtles. Population D, 30% of turtles have a shell length greater than 2 feet. Population E, 20% of the turtles have shell length greater than 2 feet. From a random sample of 40 turtles selected from D, 15, okay, we can see what's going on. 15 had a shell length greater than 2. Random sample of 60, 11 had a shell length greater than 2. So these are sample proportions, and we are looking to see, okay, the value of the difference of p hats of D minus p hats of E. So this is basically what is the value of our statistic that we're going to test. And we can figure that out because p hat sub D is going to be 15 out of 40. So p hat sub D is 15 out of 40. And p hat sub E equals 11 out of 60. All right, so we can figure out what those are. 15 out of 40 should be 0.375. And then 0.183. All right, so p hat sub D minus p hat sub E.
Wait, what value did you get for the P hat sub D?
That's 0.375.
Okay.
Yeah, sorry, it didn't look very much like a 3. So 0.375 minus 0.183 can give us our answer. So 0.192. All right. So the mean and standard deviation of the sampling distribution and difference in sample proportions. Okay. So let me go ahead and, I didn't want to clear, sorry. So I wanted to erase a little bit. So this is one where it tells us that we have a population number to work with. And this is one where the mean and standard deviation of the sampling distribution of the difference in sample proportions. When we don't have a population number to work with, then we use our sample proportions. But when we have a population number, we work with that. So the mean is going to be the mean of D minus E will be 0.3 minus 0.2, because in population D, so P sub D is 0.3. And one thing we learned is that the mean value of D is going to equal the population proportion. So it's basically just going to be 0.3 minus 0.2. I don't know if that completely followed, if I made myself clear enough. Are there questions on that idea? I might not be.
That's the mean is 0.1?
Yeah, the mean difference we should expect is 0.1. And then the standard deviation is going to be, That's D minus E. That's the combined variance. So it's going to be 0.3 times 0.7. This is where we're doing our, maybe if I write the generic formula real quick, it's going to be P sub 1 minus P sub, or times 1 minus P sub 1 all over N sub 1 plus P sub 2 times 1 minus P sub 2 all over N sub 2. So I'm just plugging my values in right here. My sample size for the first one is 40 turtles. So it's going to be over 40 plus, it's going to be 0.2 times 0.8 divided by 60 turtles. And then we can do that math and figure it out from there. That's what the sampling distribution is going to look like. It's going to have a mean of 0.1. So if here's 0.1, it's going to be centered around there. And the standard deviation is what we can calculate. And then they want us to check the assumptions right here for this to make sure that for this sample, for this sampling distribution, candidate be assumed to be approximately normal. We want to check the large counts condition. So does N1 times P sub 1 and N1 times 1 minus P sub 1, are those both greater than or equal to 10? And do the same thing for part 2. Okay. So they're basically at this point asking us to determine what is the p-value for getting this particular result. So what's the probability that this sample difference is greater than the value found in part A? So we're going to have our stat 0.192 minus a parameter 0.1 over the standard error that we calculated, which was that long one that we just did, 0.3 times 0.7 all over 40 plus 0.2 times 0.8 all over 60. And then you can figure out what that z-score is. All right. Are you guys feeling like this is making any sense, or am I thoroughly confusing you? Okay, I'm good. All right, now if any of this didn't make sense, I would love to go over this in more detail, especially, let me say this, those of you who are doing the AP test, I am available every day before and after school, and what I highly encourage you to do is to do the practice tests that I have available on, well, I can make sure that they're available online, but all those review packets that are there, I highly encourage you to go through them and come to me with questions that you have, because I won't necessarily be able to answer them in great detail during class, but if you come before and after school, I'm more than happy to sit with you and we can go and, go into more detail, spend more time going over this stuff. There.
You have Eli? Hi.
Oh, yeah.
Okay, can I borrow him to set up his AP test?
Okay, confidence intervals. I'm just gonna bring all this stuff up. All right, so unit 8 was just the first inference test that we introduced. We had confidence intervals for one sample proportion or one sample mean. And we have a general formula, again, straight off the AP formula sheet, specific formulas when we plug in the correct values for the context. And our 4-step process was basically state, plan, do, and conclude. We ran through this. We might not have emphasized those particular terms right here, state, plan, do, conclude, but we did run through the same process over and over again, where with the planning, that's where you're checking your conditions, stating, you're saying exactly what you plan on doing. If it involves setting up hypotheses, you would do it there. Do is where you show your work. Conclude is where you write out your conclusion sentence or pair sentences. Interpreting. It's important to know how to interpret confidence level and confidence intervals. So confidence level says that if we repeated this over and over and over again, we would expect 95%, if it's 95% confidence level, we'd expect 95% of our confidence intervals to contain the true population parameter of interest. Okay. So this is already, we're talking about a correct interpretation of the interval from 41.18 to 42.363. And this is the 90% confidence interval for the mean number of hours worked per week for all employed adults. I'll let you go ahead and answer this one, but I'll probably just start skipping through the problems and kind of answering them quickly to save on time. In this particular problem, when you substitute in your number here is 0.6, when you have 180 out of 300, and your Z star is 2.326. You have to look that up from your table B in your guide, so in your formula sheet, so times 0.4 divided by 300 in the sample size. When you go through and do all that, you will get C as your answer. Okay. So let's look at this. This is one where they give you, okay, the same district, varsity for it, 95. Okay, what is the standard error? The difference. Okay, so they actually want us to do a 2 sample Z interval for this. And technically this isn't something we did until unit 9, but to be fair, it kind of all blends together. So if we've got P hat sub 1 is 16 out of 85, and P hat sub 2 is 19 out of 67. The only thing they're asking for is the standard error. So the only thing we need to calculate is this. And this is just a general formula, which is going to be, and this is where it gets a little bit weird. If we're doing a difference of proportions, we keep these separate. If this is a 2 sample Z test, then the assumption is that it comes from the same population, so we would pool it. But here we actually don't pool it for a 2 sample Z interval. So we would still do whatever 16 divided by 85 is. 16 divided by 85 is 0.188, and 19 out of 67 is 0.284. So we would keep these as 2 separate proportions, and I would do 0.188 times 0.812 all over the sample of 85 plus 0.284 times 0.716 all over 67, which is a sample size. That's the only calculation we need to do for this. So as complex as this might be, if we had to do even more, it's really just that one calculation in order to figure out the standard error. I shouldn't have put this. That would be technically just that. Okay, and that math we can work through and figure it out. All right, so one thing we can rule out right away, it's not going to be this, and it's not going to be that. Those are way too high. So your difference in proportions is likely to be something, in this range. But there we are. I'm actually not going to worry about the answer from there. I'm just going to move forward because I want to look at unit 9. In fact, I will skip past this stuff. If you have more questions about it, I encourage you to look through those practice problems. And of course, we can look over any of those that you still have questions on. Unit 9 was hypothesis testing. Okay. And then just all things related to hypothesis testing, I won't really go through it. Here's your 2 formulas that we used to figure out a test statistic if it's a difference in, or if it's a sample mean. Here's the test statistic if it's a sample proportion. And I should add that that should actually be P, not P hat. Okay, and well, it should be P hat if we don't know the true proportion. Anyways, sorry. Type 1 and type 2 error and power was another topic that came into play here. All right. And I want to be careful on like what I go through with this because I don't want to go too fast, but also not too slow. So I'll just let you guys look at this and come up with your best answer without me talking. All right. And the answer here is E. Everyone who answered got the same one, and so that's good. And we are seeing that the p-value is higher than our significance level. And we know that we only reject the null hypothesis if our p-value is below the significance level. So because the p-value is greater, there's not convincing evidence that the population mean number of ounces dispensed into a bottle is less than 12 ounces. So you're looking for this not convincing evidence sort of statement. All right. All right. I'm going to go ahead and let you guys try and answer this one as well. When we're dealing with power, remember the power is the probability that we will correctly reject the null hypothesis. And you get the biggest power when, if here's your null hypothesis distribution, if the actual value is much higher, and so you have very little overlap between the true value and what your null hypothesis is, then you will have higher power. So basically, this is called your effect size. So the bigger the effect size, the more power it's going to have. So we want to have, if the null hypothesis is that it's 20%, then, or the null hypothesis that it is 20%, then having a number further away from 20% is better. So 50% would be the way to go. The other thing is that when you increase your sample size, you are getting a narrower distribution. So if I have a 1,000, it might look like this and like this, as opposed to the previous one that I drew. So that's going to increase the power so where there's basically no chance we're going to fail to reject the null hypothesis. So in something like this, I would say there's probably about a 100% power in a test that looks like this. Okay. All right, checking your conditions. You guys can try this one. We can see that this is going to be a skewed distribution because most customers have 0 payouts, a few have substantial payouts. So we're looking at a distribution that might look like this, skewed. And that's okay as long as you have at least 30 in your sample size, but we don't. So the distribution is skewed and the sample size is not large enough to satisfy the condition. All right. So let's see if we can skip any of these. This is just setting up and calculating your test statistic. Let me see, is this something? You know what, this one's worth looking at, but maybe I'll just talk through this one real quick. They already give us the test statistic. So the entire thing where we're gonna have to figure out your X bar minus mu divided by, it's proportion, so I'm doing the wrong thing, whoops. So it was going to be z equals p hat minus p all over this calculation. That's already been done for us. We already know that z equals 2.25. So the question is, what's the p-value, knowing that that's our test statistic? Well, since it's proportions, we're going to use a normal CDF calculation going from 2.25, our z-score right here, up to positive infinity. So we want to figure out the p-value. Really, all they're asking us to do is find the area under the curve. All right, so if we do that, normal CDF, going from 2.25 to positive infinity, I got 0.0122 right there. All right. let's see how many more questions I have. Okay, what's that? 4 more? 1, 2, 3. Just 3 more. Let's see. This is a good one for us to look at. Which is, the following describes a type 1 error. So look at that and see if you can find the type 1 error. Type 1 error is when you incorrectly reject the null hypothesis. You rejected the null and you shouldn't have. If you think back to the boy who cried wolf, the townspeople rejected the null hypothesis that there was no wolf because he said there was one. So they committed a type 1 error by rejecting the null hypothesis when they should not have. So the answer is D. So the test says that it's less than 12 ounces, but in actuality, it's at least 12. So B is the one you pick for type 2 error. Yeah. Okay. All right. Another question about power and type 1, type 2, all that fun stuff. So look at that one real quick. So I'm going to draw a picture to help explain this one. There's the null. There's the true value. So if your significance level is right here and it says that only when it falls in this range are we going to reject the null hypothesis. All right. Well, if we bump this up to now where it has to be even further, like we're decreasing the significance level. And that means that we have a higher chance of failing to reject the null. Because we moved it, if the original one was sitting right here, what we did is we just went from this area of a type 2 error, and then we added this onto it. So what we've done is we've actually increased the probability of a type 2 error by making it harder to reject the null hypothesis. So you can think of it that way. By making the significance level smaller, we made it harder to reject the null. And that increased the probability of a type 2 error. So I'll put the type 2 right here. Probability went up. And when that goes up, your power goes down. So the answer is E. So your power went from, I'm changing colors so you can see. It went from this right here to this right here. Okay. Any questions on that? Okay, fun times. Last one. So this is a kind of a strange question, but maybe to make sense of this, we need to remember that your significance level is the same as your probability of a type 1 error. All right, and if you do remember that, a type 1 error occurs when you reject the null hypothesis when the null is actually true. So that's maybe the most straightforward way. And now we're basically, you can convert that into a sentence, and that's exactly what A says. The significance level, alpha, is the probability of rejecting the null hypothesis when the null hypothesis is actually true. So that's what we're saying. And just to put this into kind of graphical or kind of a diagram term, something like that, here's your null hypothesis. So whatever, P sub naught. And you're thinking that this proportion is actually true. It doesn't matter the context here. So you set a significance level that says, only if it falls into this range am I going to reject it, because otherwise it could happen by random chance. Now, even by random chance, you could get a result that falls in that range right there. But that doesn't mean that your null hypothesis is false. It just means that you happen to get one of those samples that happened to be in the rejection range. So there is a chance, even when you reject the null hypothesis, that you made an error. And sometimes we don't know if we made an error or not. But the probability of type 1 error is just the same as your significance level. So 2 different ways of thinking about that problem. And I have some more FRQs available. Remember, doing the FRQs and submitting your work is optional. but I highly encourage you guys to look through it. And we will, it says we're going to review 10 and 11 tomorrow. Certainly 10, and we'll see if we get through 11 also. But we just tomorrow and Wednesday is the last of us going through stuff. And then, like I said, after this week, things really settle down, after your AP test especially. But if you have any questions on any of this stuff, make sure you're getting help from me. And yeah, good luck with all that.